The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. Welcome to Halifax, Nova Scotia, and Nautel's seminar on -10, -14 HD radio solutions. I'm Chuck Kelly. I have with me a distinguished panel of Mike Woods, Head of Development of Nautel. Mike.
Good afternoon.
And Philip Schmidt, Research Engineer here at Nautel.
Hello.
And we've got a very interesting presentation. We've analyzed the group of people that are logged in, and we know what percentage of people have been to one of our previous seminars before. We know which people haven't been to those. So we are going to cover some older material, but we'll go through it relatively quickly. We're going to talk about why we're talking about an increase in HD power level. We're going to talk about the various different types of alternatives to upgrade your system to a higher injection level. We're going to talk about the specific technologies that Nautel has developed to innovatively allow you to get more out of your system at better performance. And we're going to take your questions. You'll notice that on the GoToWebinar system that you've got there in front of each of you, that there is a place you can put questions, and we will be able to read those and be able to answer them at the end of the webinar. So feel free to type questions in there. Just as a little bit of an explanation, Nautel is 40 years old last year, and we're very excited about that. We've never done anything but solid-state transmitters, and it's a very innovative company. You can see our company, the employees on the right-hand side of the photograph. We're right on the shores of St. Margaret's Bay, which is actually quite a beautiful place here in Nova Scotia. So the first question becomes, why do we want an HD power increase? Why has the industry been waiting for this? Well, this HD power increase provides for better building penetration. It improves outdoor coverage to the 60 dBu contour or beyond, which means that you have less blending back to analog and less multicast dropouts. And you have better reception on receivers that have less than ideal antennas, like portables. One of the things that has caused this is the fact that worldwide, there has been an increase in the noise floor in the FM and AM bands, but we're going to focus at the moment on the FM band. So a lot of new technologies have come along, and what it basically means, as opposed to 30 or 40 years ago, there's dozens and dozens, if not hundreds, of little transmitters inside of your offices and your buildings and your car and down the street. And those cause increase in the ambient noise floor that the radio station has to operate within that environment. So if we talk about the signal-to-noise environment, we can see the classic IBOC schematic here, the classic diagram. You can see the orange-colored HD radio sidebands and the simplistic analog FM signal in the middle, and the reception noise has gone up. Now, in this situation, you're probably still okay. But what if the noise floor continues to rise? Now I can continue to hear the analog because of the capture effect of an FM radio, but the sidebands are gone. They're buried in the noise. So these are the kinds of scenarios that we're trying to counteract. Here's a very real-world example. There were tests that were done. I think this was NPR that did these tests originally, under conditions of -20 dBc, which is the standard injection level that has historically been used in FM HD. And you can see where, when they were driving, where the coverage was green, they had perfect HD signals, and where it turned red, less than perfect HD signals. So as they increased the injection level by 6 dB to -14, you can see a much greater area of green. And then at -10, you can see, again, almost a perfect signal, equivalent or greater than the -60 dBc contour for the analog. So let's talk about the timeline. The first experimental testing period of -10 dBc was in 2007. Then in 2008, there was a request of the FCC to increase power by a number of stations as well as Ubiquity. The NPR Labs report said that 1% was not enough, but that 10% was potentially too much. There was an FCC public notice, and then last year there was a lot of activity. There was a metric developed by NPR Labs for determining interference. The FCC issued their second public notice. They wanted to figure out whether or not they should wait until after the NPR studies were done. Finally, the NPR Labs report was given to the FCC, which detailed the impact of mobile interference, and then finally, Ubiquity and NPR Labs jointly submitted a 5-point proposal to the FCC last year, and then early this year, the FCC approved the power increase. So now, this is where we are now. We've got an approved report and order from the FCC. This provides for a blanket 6 dB increase for all the stations except for Super B and C stations. Beyond 6 dB, up to 10 dB, which is subject to a formula developed by NPR Labs. There's a procedure for remediation of harmful interference cases above -20. The FCC has reserved the right to revisit the issue if widespread interference does result. Note that if asymmetrical sidebands or unequal sideband levels were not specifically addressed, but it would presumably effectively be compliant with the established interference criteria in the report and order. So that means that if on your lower sideband you have less interference potential than on your upper sideband, then potentially you could run more power on your lower sideband than on your upper sideband. And since that's redundant information in the Ubiquity HD radio system, it only adds to your performance of your total system. There's also a very detailed channel protection system that the FCC has indicated. This gets pretty complicated. I would recommend that in any situation where you're trying to see how much power you could get to beyond -14, that bringing a consultant in would be a good idea. There is a very detailed complaint remediation for interference process that the FCC, which is based on the broadcasters, they're really working with each other, mutual resolution, voluntary reductions. If it gets beyond that point, if it can't be resolved at that point, there's an opportunity for seeking remediation from the FCC. There's a notification procedure. For -14, basically you notify the FCC with a digital notification form within 10 days after commencing operation. If you want to go above -14, you have to file a request showing the calculations. This is where you bring your consultant in and take a look at it. Superpower FMs must file an informal application for any proposal increase in digital power. So the very first step in this whole process is to determine how much injection is enough in your situation. So you've got to analyze your digital coverage. Are you in a high noise environment? What interference potential is there for other stations? Interference to your own analog signal. It's possible if you increase your digital enough, it could cause interference in your own analog signal. And then you need regulatory clearance beyond -14. In every one of these cases, again, especially if you're looking beyond -14, a consultant would be very helpful. So let's talk about the various ways, once you've decided what level you're going to go to, the various ways to implement that upgrade within your station. We'll talk about each of these choices, antenna upgrades, digital-only boosters. It's not really boosters in this case, we're talking about digital-only solutions, and then separate digital transmitter, higher-powered hybrid mode transmitter, and also we'll discuss HD Power Boost. So one possible way of going, suppose you're in a hybrid condition today. You're in a hybrid situation, you're doing -20 today, and you want to go to a higher injection level. One possible way is to increase the antenna gain, add more bays or change your antenna, which lowers the necessary analog TPO to hit your final power output of the station, ERP. And then because you've bought some room under the headroom of your transmitter, you can increase your digital injection, and it's relatively inexpensive, potentially, a relatively inexpensive way of increasing the performance of your station. Considerations are that a bigger antenna requires more space in the tower. It has wind and weight load implications. Making sure that the performance of the antenna, if all you've done is add bays, that the impedance and everything else, the performance of the antenna is correct. You've got to look very carefully at the coverage and antenna nulls. And probably another thing to think about is, since in effect with the hybrid station you're actually raising the sidebands up by up to 10 dB, 6 dB or 10 dB, the requirement, if you weren't passing the mask with a lot of room before, you're going to have trouble going forward, because by bringing up those digital sidebands, if you don't have a lot of room under that spectrum mask on the shoulders, as we say, of the FM signal, then you're going to, you may have troubles meeting the mask. So you've got to pay attention to that point too. Probably the last step in any one of these implementation scenarios is haul out a spectrum analyzer and verify your spectral performance. Another possible way is to use high power combined. The problem is, as you go to higher power injection of the digital signal, you get far more power as you change your injector from a 10 dB hybrid down to something different. You end up with much more analog power going into the reject load. And in this case, as we've shown, the analog power going to the reject load is actually as much as 30% of your analog transmitter power. That's a lot of power going into a reject load, a lot of wasted power, a lot of wasted electricity, a lot of heat generated into the room. If you go with space combination, that still works. Power in building space is the issue. Analog versus digital radiation pattern differences. It's a very interesting point. If at 20 dB, or the normal HD power injection level previously, there was differences in the pattern of the analog antenna versus the digital antenna, the possibility of causing interference from the digital into the analog was relatively reduced. By going with a higher injection level in a space-combined situation, the headroom you've got before you start interfering with the analog is reduced. So if any variations in the pattern performance of the analog antenna and the digital antenna are much more likely to cause you analog to digital interference, or conversely digital to analog interference. There is also RFIMD issues. You may need higher power filters. Circulators may be involved. You need to verify the digital antenna's ratings. You're multiplying by a number of times, or maybe up to 10 times the digital antenna power. And you'd have to look at that both in terms of its power capability, in terms of watts, but also in its voltage capability.
And the feeder cable as well.
That's right. And also you need to look at, there are new developments in digital-only transmitters. So for instance, in our NV20, you can get up to about 11 kilowatts of digital-only power out of that transmitter. So that's another way of accomplishing this. Now we talk about higher power hybrid situations. A hybrid scenario is probably now, given these higher injection levels, more practical than the other scenarios were because of these issues that we've talked about already. It's simple architecture, single box installation, minimizes the amount of transmitter footprint in the room, minimizes antenna problems and tower problems. The higher injection level may reduce the analog TPO capability, but we'll talk about that. We may need to replace your transmitter or combine with another for higher total power. And higher injection levels may reduce efficiency, but there's an answer potentially to that, which is HD power boost, and we'll show you that. One of the things we're going to do today, just to whet your appetite, is we are actually going to see a Nautel transmitter in operation and make some changes and change from one mode to the other, so that'll be fun. I mentioned that the efficiency goes down as the injection level goes up. These are some graphs that show approximate levels for that. So there are implications of changing a transmitter which was designed for analog or for -20 to -14 or -10 or anywhere in between. And those limitations are the linearity of that transmitter, which can be partially offset by adaptive compensation, and also the thermal dissipation of the transmitter will also limit it. So we've done a lot of work analyzing our newest series of transmitters and even our V series of transmitters for compatibility with these higher injection levels. And you can see some of the setup there. We're looking at temperatures, we're looking at spectral mask, we're looking at all sorts of things. And one of the things that we've done is, this is a transistor actually a FET right in one of the amplifiers, and we can switch to an IR camera, and we can actually take the temperature of the silicon while it's in operation and really see how this transmitter is performing and where we have issues, and make sure that we've got the headroom in the design to be able to accommodate these higher injection levels, not just theoretically, but actually prove what's going on. So we're going to talk about HD power boost, we're going to talk about asymmetrical sidebands, and we're going to talk about how the flexibility of the NV series high power solid state works out. HD power boost, and many of you may have read the papers that Philip has written on the subject, and unless you really enjoy rotating vectors, it's a little bit complicated, but basically it's a Nautel innovation which applies peak to average power reduction techniques to the entire transmitted signal. The Ubiquiti HD radio system, the iBox system, has a PAPR system built into it, but it only affects the digital sidebands. When the digital sidebands increased in power level, Philip came up with the idea that we ought to really look at all of those signals, including the analog, all at the same time, and apply a PAPR algorithm to the entire process. And the HD Power Boost is actually a suite of tools that mathematically analyzes the signal and then optimizes its performance within our transmitters. And it provides up to 30% improvement in the digital power output of a transmitter in the same power transmitter. And at the same time, it provides higher efficiency, substantially higher efficiency. Mechanically, it's upgraded hardware for the NVE exciter, and then there is an optional software suite which is implemented in the NVE exciter. In many stations, the return on investment is less than 2 years in simply the electrical savings of the transmitter. Pricing on this isn't the first time we've explained this. Pricing on it is $5,000 up to 10 kilowatts and $10,000 above 10 kilowatts. And we will expect to be shipping these within the third quarter, which is just a few months away, in the third quarter of this year. And it does it without deteriorating the signal. We are still passing all of the specifications for iBox by at least 2 dB. Is that right, Phil? And the scope of the explanation of why all this is true is well beyond my capability of explaining it, and probably within beyond the timing that we have available to us today. But suffice it to say that an awful lot of research has been done, and this technology actually provides both the additional power and the additional efficiency without impacting the cleanness or the clarity of the signal. So, the next thing to discuss is asymmetrical sidebands, also known as unequal power sidebands. Bear in mind and underline that this is not yet FCC approved. The FCC, as I understand it, has not issued STAs for this yet, but it is apparent in looking at the way the rules have been written that somebody at least is thinking about this. And this capability is now possible with the NV series. With the, if you've got HD Power Boost, you also then will have the capability of setting one set of sidebands, say the lower sideband, to -14, for instance, and the upper sideband to -10, for instance. And this allows you to maximize your signal coverage while staying under the levels that would cause interference to adjacent stations.
And still taking advantage of HD Power Boost.
Absolutely.
Algorithms.
Absolutely. Let's just do that. Let's go. First off, I want to show a calculator that we've got that allows us to effectively determine the capability of the NV series transmitters in terms of its HD power injection level. And we've tried to do this before. A few months ago, we had another webinar, and it was a much simpler version of this calculator at the time. And what we've found is there's a lot of variables. If you really want to optimize the power of the transmitter, there's a lot of variables there. So with this calculator, you can see here the values of the amount of power that the NV series transmitter, shown here on the left side, can reach at the various injection levels. So for instance, an NV10 can get up to 9,900 watts at minus 20. And at minus 10, it can get all the way up to 5,625 watts. Now, let's change some things. That assumes that the maximum VSWR that we expect to encounter is 1.2:1. Pretty good antenna system. But if we change it, for instance, to 1.5:1, the numbers fall. That's obvious. When you have a higher VSWR, you make the transmitter work harder. So now an NV10 is good for about 9 kilowatts. And at minus 10, it's good for 5,119 watts. Now this is all at 98 megahertz, which happens to be a sweet spot. If I change frequency to another part of the band, say 108, one of the band extremes, the power level will fall. The other thing that impacts the power we can get out of the transmitter is the HD mode. So MP1 was the original introductory mode that HD radio was introduced with, but some stations these days, particularly those that are really using multicasting, have gone to MP3 mode, which increases the number of sidebands in the signal. Well, it stands to reason. If you increase the amount of power in those sidebands, you're certainly going to increase, and the number of those sidebands, you're going to increase the demands on the transmitter, and the effective analog power that you can get with a particular transmitter at a particular injection level will change as well. So what we can do now is, if you can provide your Nautel salesperson this information, whether you want HD power boost or not, what the VSWR capability you need is, your HD mode, and your frequency, we can tell you which power transmitter can provide what amount of power at your particular desired injection level. Let's look at for a second. Let's go back and put this thing back to 98 megahertz for a second. In MP1 mode, 1.2:1 VSWR, and let's take a look at these numbers. Choose one for your interest. For instance, an NV40 is making 39.6 kilowatts at minus 20. Or let's look out here. At minus 10, it's doing 22.5 kilowatts. Let's turn on HD Power Boost. That's now the new power. So we can do 28, almost 29 kilowatts of power in an NV40 with HD Power Boost at 98 megahertz with a 1.2:1 VSWR and an HD mode of MP1. So this calculator now, this analysis tool, is available with all of the Nautel salespeople to assist you in determining what power levels you need. Now let's go, and we're going to log in to the AUI of a transmitter, of an NV10 transmitter that is currently operating in Nautel, downstairs from where we are at the moment. And we've got an NV10 here, which is operating at 8.75 kilowatts at minus 20 injection level. And Phil, right now we've got some amazingly clean skirts here.
Yes.
The reason for that is because we intend to change the injection level and we need the headroom, right?
Exactly.
Okay. So go ahead and work some magic here. And let's go to minus, what, 10?
Yeah.
Okay, let's go to minus 10.
Well, let's stress that this is the standard system, the way it is shipping today,
Without
power boost.
Right, without power boost. All right.
First, let's switch to...
This is the actual AUI that is part of the of all of the NV series, and this AUI, Advanced User Interface, provides a tremendous amount of information. We happen to have a spectrum analyzer gadget up on the screen. I can put that into a smaller window, and I can look at a number of things: the AM to AM correction, AM to PM correction. I can look at waterfall graphs that is showing the performance of the system. Phil has now switched into the minus 10 mode, so I'll go ahead and put this back to full screen. It takes some time. Things are dancing around a little bit here on the spectrum analyzer, but eventually it's going to stabilize, and you're going to see the performance of the transmitter.
We don't start averaging until several seconds after we turn on, just so that it's a clean.
There we go. Now we're averaging.
Yeah.
And you can see we're meeting the mask by probably 5 dB. Probably. Yep. And so this is now, if we look here, we're getting 5.6 kilowatts of forward power of analog. Over here on the right-hand side, you can see that the total RMS forward power is 6.15 kilowatts, which happens to be what happens if you add the analog forward power of 5.6 plus 10% of that, or sorry, 10% of that in the digital forward power. So you can see we're really operating at minus 10. You can also see that the efficiency of this amplifier right now is about 54.5%. This is DC efficiency from the DC bus to the RF power output. So we're running about 55%. Phil, would you like to switch on HD Power Boost for us?
Sure enough.
So all these meters are defined here in the system. You can choose which ones you see. Phil is running a different screen over here, and he is making these adjustments. The transmitter is off at the moment, and he's
I think
switching
that's important to point out. Phil's logged into the transmitter as well.
That's right. We have the capability of having multiple people logged in simultaneously.
And so he's turning it off to facilitate turning on the power boost.
Right. Obviously, you wouldn't.
You can't do it on the fly.
You wouldn't be switching back and forth between these important modes on the fly. Okay, so now we can see that with HD Power Boost enabled, we are running at 7.24 kilowatts, 7.25 kilowatts at minus 10, and pretty soon it's going to start stabilizing and let us get underneath the curve. You can see here that our efficiency has gone up almost 10 points.
Right.
Almost 10%. The efficiency has gone up. And the interesting thing about that is when the efficiency goes up by that much, it also reduces in a huge way the amount of heat going into the room. So you're actually saving money twice. You're saving money in the power that is consumed by the transmitter, and you're saving money in not having to exhaust that power from the transmitter room.
Correct.
So that's pretty cool. Now, Bill, can you wave your magic wand and let's go to unequal power. I'd like to have that for me.
We will do that.
Okay.
Give me one moment there.
I'm also going to show folks that the spectrum analyzer has a lot of different functions here. I can change from, right now I'm looking at the transmitter output, and these are the averaging specs and things, but I can also switch over, for instance, to an audio analyzer, bring that up, and now we're looking at DC on the left-hand side up to 100 kilohertz on the right-hand side. In essence, the baseband signal. And here you can see my left sideband suppressed carrier L-R here as well. So let's go back to the RF because Phil's done with getting our unequal power distribution up. And we'll go back up to here. Now, as we start to converge and solidify our lines, you can see that the left-hand sideband is much lower in amplitude than the right-hand sideband by about 6 dB. And so what you've done for us is the left-hand sideband is at minus 14, and the right-hand sideband is minus 10.
That's right.
And you can see the efficiency is even a little higher than it was before because we were operating at minus 10 on both before. Stands to reason it would be a little bit higher in this particular situation.
Peak to average a little bit less.
It's important to point out at this point that the unequal sideband configuration is very closely coupled to the HD Power Boost operation,
Right.
Which is something that we have done in our implementation. Ubiquity has not considered that yet. So this is why we can get this additional power savings by dropping one of the sidebands. That is not a given in the standard mode of operation.
So when even if you're not cleared by the FCC, or nobody's cleared by the FCC to do unequal sidebands, that feature and function would be available to you if you have the HD Power Boost software on your Exciter.
Right.
Okay, so now let's talk about going back to here, and let's continue on. What did we do to do HD Power Boost? Phil, a couple of years ago at the NAB, you demonstrated HD Power Boost before a number of either odd or confused people. And you use this darn near a Cray computer to pull it off. It was a quad-core industrial PC?
8 cores.
8 cores.
It's an 8-core AMD Opteron.
Holy cow. Okay. And what you've done in this intervening period, you haven't been sitting down doing nothing. What you have done is to actually take that technology, take that processing power, and drop it into a couple of chips that you can drop into the existing exciter card. And going forward, those exciters will have that processing power on the card. You still buy the optional software to enable it, but the processing power going forward is going to be on that card. And people who have NV transmitters currently, purchased before, will be able to upgrade to that as well by changing that card. That's a pretty huge improvement. All right, let's talk about exactly how much savings we're talking about. If you have an NV40 transmitter, and you simply talk about the efficiency of that transmitter and what amount of savings is available, if you're operating at minus 20 dB with a typical power level, you can get about $2,600 a year in a 24-hour-a-day operation, 7 days a week, 365 days a year, $2,600 in estimated total savings. If we go, if you're going to operate at minus 18, you can get about $3,400 in savings. And all the way up to, at minus 10, is where the biggest savings are. You can save up to about $6,300 a year. Well, as we mentioned, the cost of HD Power Boost for a 40 kilowatt transmitter is $10,000. So in less than 2 years, with typical electric costs, you're going to save enough to pay for that HD Power feature.
And just so there's no confusion, the chart you're showing here is AC to RF.
Correct.
And the screen of the transmitter was showing DC to RF, so there's, you know, the power supply efficiency is the difference.
That's correct. And potentially some, no, it's not combiners or anything like that. It's just the power supplies. That's all the only difference. Okay. Very good.
Well, any ancillary equipment.
Right.
Yeah.
So all of this is possible in the NV series. For those of you who haven't been to one of our previous webinars on the NV series, it's a series of transmitters that starts from 3.5 kilowatts, goes up to 40 kilowatts in a single cabinet design. Very small footprint, high efficiency, and it uses the integrated NVE exciter. It comes equipped with the AUI, and it basically can provide an excess of, in a 2 cabinets installation, a combined transmitter, up to 88 kilowatts of analog power, up to 60 kilowatts of minus 14 dB, actually more than that, and 42 kilowatts at minus 10. So it's a tremendous power capability in this series of high-power solid-state transmitters. Some of the innovations of the transmitter is it's high power with no tuning, no tubes, redundancy. There's almost no single-point failures in the whole system. It's available if you want with 2 exciters. You can have all of it. It's standard with double power supplies in every situation. There's an IPA on every single power module, so even the IPA is not a single-point failure. There's advanced instrumentation and control. You've seen some of it. The spectrum analyzer built into the system, tremendous amount of metering and logging control, all of that available via the internal web server, so you can see it anywhere you are. There's improved turnaround loss so that you're less IMD problems in a situation where you've got a combined transmitter site, less need to buy filters, 100% remote access, and we've shipped almost 400 of these things in only 18 months. So it's one of the most successful new product introductions in an FM solid-state transmitter ever. So in summary, the HD injection level requirements range from minus 20 to minus 10, depending on the noise environment. The good news is there's a wide range of increased digital injection strategies which exist. Nautel has a single box solution, which is the NV series, for up to 44 kilowatts of analog and 34 kilowatts at minus 14. And you can buy for -20 and get up to -14 with HD Power Boost. So if you size an analog transmitter or an NV transmitter to do -14, you can get to -20. You can get to -14 just simply by buying the option for HD Power Boost. I'd like to talk about some upcoming events. We have a webinar in, I guess it's a little over a week, or it is a week, on the new VS series, the 31st. Today's the 24th.
April.
Oh no, it's actually March. That's a typo. Sorry about that. There's a webinar on March 31st on the VS series, so you can join that webinar in the same fashion you have this one. A whole lot of very exciting things to talk about on the VS series. The very first really IP transmitter that ever exists. You can feed your audio to this transmitter via the Internet Protocol. Integrated shoutcast, integrated live wire from Axia. The opportunity for an option to integrate an audio processor directly. We have something called Orban Inside, where we take a digital DSP card that's running the Orban code and run it inside the transmitter, so the audio processors can be integrated. And we're also inviting any of you who are traveling to Las Vegas to the NAB show to our booth number C2615, and we will be very proud to show you HD Power Boost and all these new products. If there are questions, we're happy to help. Let me see if I can see if there are any questions. It looks like there may be. Okay. Nope. It doesn't look like there are questions in retrospect. So if there are questions at any time, you can email us at sales@nautel.com. There's a webinar archive. This webinar will be available on an archive within probably by tomorrow, I imagine. You can be able to watch this at a later time, download it. It would certainly invite you to contact the wide range of knowledgeable, experienced sales representatives that can assist you with all of your needs, and they already have this HD radio calculator where you can determine the power capabilities and requirements for your station. So with that, gentlemen, do you have anything more you'd like to add?
Just that I'm very excited to have the opportunity to show this at NAB and how far we've come with the hardware reduction and kind of the all-in-one solution.
It's pretty amazing. I mean, when I saw that huge computer that you had before, Phil, I couldn't imagine how you were going to productize that.
A science project or something.
Exactly.
Now it's real world. Now it makes HD adoption, it makes -14 adoption, really a realistic, endeavor.
That's right.
Yeah.
That's right, and a very reliable thing. We're not having Linux or something like that. It's operating as or Windows. It's operating as hardware.
Design,
It's an embedded hardware design. So, my congratulations to both of you, gentlemen, on a tremendous body of work which has been done here to get the broadcasters ready for -10 and -14. We look forward to your questions. Thank you very much for joining us today. For now, from Halifax, Nova Scotia, I'm Chuck Kelly. Thank you very much for joining us.